My name is Krischer. I'm the wireless evangelist for Cisco across Asia Pacific, Japan, and Greater China. And oftentimes people ask me what that actually means. What do you do? Describing my job I find very difficult, but today's like today, I think, sum it up. I get to spend a day at a pub talking about Wi-Fi. Not a bad thing to do. What I want to do, and actually I think what UC took you guys through this morning was a good way to kind of open things up, because he showed all this stuff, looking at the signals, talking about understanding what's going on. And I want to take a step beneath that. What I want to look at is, how does Wi-Fi actually work at the RF level? And that's what I think makes it so interesting and yet so complex at the same time. One of my favorite quotes: any sufficiently advanced technology is indistinguishable from magic. And how many of you think Wi-Fi is magic? It really feels like that sometimes. And I'll tell you what, because you can't touch it, you can't feel it. Little exercise. Everybody take a deep breath. You've just inhaled the physical layer of a wireless network. Think about that. So how do we get our heads wrapped around this if we can't touch it and we can't feel it? Well, I really like this image, because what are we seeing here? You throw a stone in a pond, right? Those ripples emanate. That is energy, right? Those ripples. That is exactly what's happening with RF, because all it is energy. So think about what we've got. It's the electromagnetic spectrum, okay? Radio waves, microwaves, really good for making popcorn and interfering with 2.4 gig access points. But even light is electromagnetic radiation. And when we think about that, right, the different colors, the reason we have these different colors is how our eyes and our brains perceive this energy, which is transmitting at different frequencies with different wavelengths, right? It also helps understand how those waves propagate, right? Light isn't going to pass through my hand because of the frequency that they're going at. Yet X-rays will go through skin, but they'll be stopped by the bone. That's why we use X-rays to take photos to see what's going on in our body. But that helps us understand how these waves are going to propagate through space and the impact that they might have. So let's look at some of the fundamentals. So we talked about frequency, we talked about wavelength. There's actually a relationship here, right? F, the frequency, equals C divided by lambda, the wavelength. Who can tell me what C is? Speed of light, exactly. Speed of light in a vacuum. But think about this, right? These are real physical lengths, right? 2.4 gig, that's 12 centimeters wavelength. 5 gig, 6 centimeters. This is tangible, right? This is real. This is, about the size of your phone, which, by the way, is why it's hard to cram a lot of antennas into a small device, because how'd that happen? I want to keep things, right, relatively space between in that way. We can talk about the amplitude, right? That's the height, or what I like to view it as the volume of the signal. And then phase, right? How that wave is shifted in time. Okay? So those are kind of the three basic principles in how we would define a wave. Now, what you saw on that screen is really looking at what's happening from the signal. So we really focus on signal strength. And we're going to talk about gains and amplification and losses and attenuation. And what we're really looking at is, how do these waves propagate? Okay, so we'll talk about attenuation and free space path loss. Right? When we take a signal and go to an external antenna, we lose some of that energy over that wire. That's attenuation. And then those signals are going to be moving about in space, and they're going to be impacted by things. Right? And so we look at the impact that has. All right. Now, when we think about how those signals are spread, right? We're also looking at the inverse square law. So think about blowing up a balloon. Okay, that balloon expands, and the rubber gets thinner and thinner as you put more air in it. Well, that's what's happening to the energy. As it expands out, right, we're going to lose it over a larger area. So now we come down to like the math part. This is the bit that always gets me when you look at those tools like the Echthouse tool, right? Everything's in negative numbers. What is that? that mean, right? Negative should be bad. But what we're looking at is logarithmic scale, right? That's partly why the math is all kind of weird. So we talk about decibels. All decibels is a ratio of values, right? Voltages, powers, gains, and losses. So we can add the gains and subtract the losses. So we talk about dBm, right? What is that? That's just a power measurement relative to 1 milliwatts, right? And then for antennas, we talk about dBi. Well, what's that? That's basically the forward gain of my antenna relative to an isotropic antenna. Now, who can tell me what an isotropic antenna is? Yeah?
Theoretical antenna with basically a dot.
Perfect. A theoretically perfect antenna. Why theoretical? Well, it's actually physically impossible to make a perfect antenna. Why? Because I need to get energy into that antenna so it will radiate for me. And that connection, where I'm putting in that wire, that is what causes the imperfection. We'll take a look at that a little bit later. So, here's a couple fundamental points to think about when we're designing Wi-Fi based on these principles. First off, any RF signal, other than what I care about, is interference. I'm not just talking about microwave ovens and high-intensity lights and stuff like that. Another access point that's not part of my network that I don't care about. It's all interference. So we talk about signal-to-noise ratio, which by definition is a ratio. If it's a ratio, we measure it in decibels, exactly. So the signal strength is going to be related to two things. One, my transmit power, and then my receive sensitivity, okay? Now, here's a real fundamental piece to how wireless works. At the end of the day, we have two levers, right? You can increase the signal, and you can decrease the noise. That is it, right? That is all you have to make all this work, okay? And this is why, in some ways, wireless is so hard. And when we look at all the things we're going to go through, all the things that all the different vendors do, we're basically focused on doing one of these two things, helping you increase the signal or decrease the noise. So let's take a quick look at just how antennas work now, because this is important to help us understand how that energy is propagating through space, because since I can't see it, I need to figure it out at least to understand what's happening from my design perspective. So probably the most common antenna we deal with is an omnidirectional, radiating energy out in all directions. And that's what you're seeing here on the azimuth plane, the horizontal plane. Now look up at the top, not sure if it really comes out, but you can see it's not quite a perfect 360, right? That's the imperfection caused by that wire. That goes back to why it's impossible to make a perfect antenna. But the other piece is here on the vertical plane, the elevation plane, right? It's not a perfect sphere. We're actually seeing the energy cast out with these large bulbs, and this is the important piece. This is a null, which basically means if I'm in front of the null, I'm not getting as much energy. My signal quality, my signal strength will be much lower. So that's omnidirectional. We also do patch to really focus the energy in a specific direction. And here you can kind of see we're focused predominantly in front, but check that out, right? And so, if you've ever put a patchy antenna on the ceiling for aesthetic purposes, and then all of a sudden you got someone saying, hey, I'm connecting to the downstairs AP even though I'm on top, that's why. Understand how that RF is actually propagating from the antenna. Internal antennas is what we typically use today, right? Particularly for our indoor deployment. And the important thing here is to recognize that with everything we do with antennas, there's going to be a trade-off, right? So if I'm designing antennas to fit inside my access point, plus I have multiple radios in there, well, that's going to have an impact. And you can see I don't get the same perfect sphere that I had, the perfect circle that I had before. And even here, the shape is quite odd. And that's just because of all the other electronics, all the different shielding that we need to do to make that work. All right. What about dual band antennas? Well, this is another way of looking at the impact of the trade-offs. Here's that 2.4 gig antenna. Again, nice circle, as good as I can get it. Here's 2.4 and 5 gig. It's like that old ad, this is your brain on drugs. In order to get the antenna dealing with a wider frequency range, there's going to be trade-offs, and that's what you're seeing. Yeah. What about high gain antennas? Well, in this, I'm really trying to focus the energy to go long distance. So what are the trade-offs here? Well, look at this. You can see just how ragged it all is, all those nulls going in there. And this goes into, again, how I'm trying to design the antenna and the trade-offs. Check it from this angle, right? I want to go far. And so I'm actually going to design the antenna to fill in the nulls that are at that front part where the energy is. Now again, trade-offs for everything. By filling in these nulls, I make even more intense nulls further in the back. And so where I'm close to the antenna, I'm going to hit those nulls, again, weak signal. So all this is really just trying to say, understand the different types of antennas, understand how they propagate energy, understand how that's going to go. That is your starting point in a good design. Oftentimes I see people set things up, and it's like, well, you had a patch antenna, and you're trying to cover the area behind, how is that going to work? Or I've got my patch antenna, and I'm aiming right at that metal duct up there. We talk about radio resource management, all these wonderful algorithms that we do. They don't defy the laws of physics, right? You point that thing, doesn't matter what math I use, it's just not going to work, okay? So, the energy's propagating. Now, we often think in terms of direct line of sight because that's how we see, trying to relate it to things that we can. But of course, omnidirectional, signals going everywhere, and oftentimes there's not direct line of sight. So these signals are not only going to be impacted as they get to my client, but they're going to be bouncing off walls, reflected everywhere. This is what we call multipath. Now, in the early days of wireless, we viewed multipath as a problem. And I'll show you a little bit later why now we actually view it as a potentially good thing. But the reason why it initially was viewed as bad is because of this idea of destructive and constructive interference. So here's kind of these three signals that are bouncing all around. Okay? The first two look very strong, right? The third one, pretty low on the amplitude, right? Low volume, low signal strength. But the first two, they're actually out of phase, directly out of phase. So when I add them together at my receiver, I actually get a decrease in the signal quality. Conversely, the bottom two, even though this is a lower signal strength, it actually has an additive effect. So, who remembers that access point? You can tell me what model that is. What? 1242, exactly. That was our last AG AP. So, we used to use a technique called antenna diversity back then. And the idea, quite simply, was we'd listen on two different radios, we'd figure out where do I get the better signal from, and that's the one that I'm going to use. Anybody still listen to the radio? Yeah, kind of, sort of, So you stop at a red light, and the signal drops out for the station, and you lift your foot off the brake, and just inch a little forward, and then it comes back to life. You're basically implementing antenna diversity in your car, and moving the antenna physically to get that better signal. So that was the old way that we did. Then with 802.11n, we introduced this concept called MIMO, multiple input, multiple output. And there's a couple different things that we did with that, but first and foremost is this idea of diversity combining. Basically what we figured out was, hey, if I adjust for the phase of that middle signal, now when I add it together, I'm actually going to get an improvement. And so in Wi-Fi, what we're actually doing, it's called maximal ratio combining, and it's basically figuring out how to add the different signal components together to maximize the signal-noise ratio. And so that's what happened with 11n. So all those multipath signals that used to be bad, now all of a sudden are good. So I've got signals bouncing off walls, going around corners, and rather than that harming my Wi-Fi quality, now I can actually take advantage of that and improve my coverage. Sound good? All right. What are some other MIMO techniques that we got? Well, if MRC is on the receive side, what can we do on the transmit side? Well, that's transmit beamforming. I've got these two radios, two transmitters. Where the signals overlap, I get an increase in energy. So if I can just get you to move just a little bit over, that's not really going to work, right? So instead, I'm going to get the signal to orient towards where you are. Now, this is actually explicit transmit beamforming. Took a number of tries to actually get this through the standards. It was really in 11AC Wave 2 that you really started to see it in a normal sense, and so now that's what we're taking advantage of in most of the chipsets today. Again, improving the signal strength at the receiving device. One other technique that we do, and this is about cramming more bandwidth in as opposed to looking at from the perspective of our signal strength. So again, I have two transmitters. Rather than using them to send the same data, what if I use them to send different parts of the data? Well, I get a doubling effect. So that's our spatial streams, and that's a really good way of how we increase the amount of bits that I can get to send across over in the air. Which begs the question, right? These are RF signals. This is an analog signal. How am I actually sending data across this? Well, I need to encode that data into this analog signal. And that's what digital modulation is all about. So here's my carrier signal, right? There's three ways that I can modulate this signal that go back to the different characteristics, right? The amplitude, the frequency, and the phase. So let's give a very simple example, QPSK. What I'm basically doing is for every shift that represents a different symbol. So now I've got 0, 1, 2, and 3. I've encoded it into 2 bits. Okay? Very low bandwidth, but shows the basic principles. In modern Wi-Fi, we're basically using QAM, quadrature amplitude modulation. Now the interesting thing here is I'm actually modulating both the amplitude and the phase. And that's going to allow me to cram more bits into what I'm doing. So it gives me high spectral efficiency. That is, I'm making the best use of the spectrum, cramming more bits. But it also then makes it a bit more challenging to demodulate that when I've got noise. And this comes back to that really important point. I can increase the signal or decrease the noise. And this is why I need to decrease that noise. So here's what we just saw, right? So I'm going to encode these 2 bits, all right? On the receive side, this is what it looks like. This is a constellation diagram, okay? So you can see my different things. I got 0, 1, 2, and 3. This is at a signal noise ratio of 10. This is at a signal noise ratio of 6. A lot harder to figure out what the symbols are, right? So what are we looking at right here? That's a drop packet. I can't figure out what it says, okay? So that's 4 QAM that you're just looking at. That's 64 QAM. That's what we use in 802.11n. That's 256 QAM, which is what we're using in AC. Right? I need much better signal-noise ratio in order to figure out what I'm sending through. And in fact, there's a known table, right? We know that what we need. There's a direct relationship between signal-noise ratio and the different modulation schemes. And you can look it up and you know, in order to get this rate, this is what I've got to have. And so what happens is, even though I say on the sticker, hey, 1.3 gig, that's assuming that I have good signal strength and good signal quality, and I'm able to have that 256 QAM modulation scheme. If not, I've got to throttle back. That's why the data rates start to drop down. So what are some of the things that we can do to help improve that signal quality? Well, one of them is what we look at called transmit and receive diversity. And again, we're going to look at, I've got these multiple transmit receive chains, how can I use them effectively? So what we're looking at here is I'm going to do 3 spatial streams. I've taken an AP that's basically got 4 transmit and receive, but I've disabled one of those radios. So you can see here, my signal quality is quite poor. I'm not able to maintain the high data rates in the whole area. When I bring back that 4th radio, now all of a sudden I get really nice coverage there. That extra radio giving me transmit diversity is basically helping me get that clean signal to support the high data rate. On the flip side, on the receive side, think about the problem there, right? My AP is, fully powered, got big nice radios, got full visibility of the whole area if I've designed it right. My client is this small device running on battery, okay? It's not going to have as good a transmitter, not going to have as many transmit receive chains. So even if I'm running, I've got like a laptop that has 3 spatial streams, look at what happens here. If I only have 3 receive radios trying to receive these 3 spatial streams, for the most part, I actually can't sustain it. right? Because just the signal quality isn't good enough. So we end up dropping back down to 2 spatial streams. The other side, what you're basically seeing here, with the 4th radio, I have a much better chance of maintaining those data rates, maintaining all 3 spatial streams. So the answer here is we basically need n+1. Right? If you've got 4 radios, plan on 3 spatial streams both receive and transmit. Because otherwise you're just going to throttle back anyway, and you're basically losing that spectral efficiency. So, yep. Yep. Yeah, so it's the same sort of result because at the end of the day, it's just how I'm able to hear, and that diversity is what's helping me get that improved. So one last piece that we need to look at in all this, and I bet you didn't think you were going to be talking deep RF first thing in the morning. Oh wait, it's a Wi-Fi conference. I guess you did think you were going to do that. Okay, OFDM. What's that? We hear about it a lot. That's basically started with the 11A days, and it's what we use. It's multi-carrier modulation. And again, all this is about how do I cram more bits into the signal. So the idea is we're going to combine both modulation and multiplexing. And so we've got our transmission channel. I'm going to divide it into subcarriers. I need to have them orthogonal to each other in order not to interfere, and that's where O in OFDM comes from. And basically, you didn't realize it, but it's really the foundation for Dark Side of the Moon. I find it very easy to visualize. You can tell who the young people are. They're like, Dark Side of the Moon, what's that? You've seen the t-shirt. Anyway, right, we're looking at the separation of the light into different colors. That's my subcarrier. And what's cool is I then can modulate each one of those subcarriers using my quadster amplitude modulation. Right? So this is how I'm cramming more data, more bits into the signal. So that's kind of at the modulation scheme. What other techniques do I have? Well, one of them is channel bonding. Our basic channel is 20 megahertz. You saw those channels UC had up. I can do that channel bonding, and that's what we saw. Now, they showed you how bad it was to do 40 megahertz channels in 2.4 gigs, so we really don't like to do that. We like to do a 5 gig. And then we look at creating 80 megahertz channels. That's what we got with 8 to 11 AC. So here's our 2.4 gig. Basically have 3 usable channels. Again, why we don't do 40 megahertz in there. 5 gig, we've got a lot more channels to play with. But it's going to be limited based on what country you're in and what the regulatory domain is. So this bit here, this weather radar area, for those of you who know Cisco AP SKUs, the -Z SKU, basically is because of that weather radar area. We aren't allowed to use it. In the US with FCC, they can. But the other piece that you're seeing then is, how many of these bonded channels do I have available? And so we don't even have that many on the 80 megahertz. 40 megahertz really ends up being the sweet spot, depending on how dense your deployment ends up being. So let's look at this now at the protocol level, right? So 8 to 11 AC. First off, 5 gig only. How many people knew that AC is 5 gig only? All right, good to say. So if you've got an AC AP with a 2.4 gig radio, effectively 11N on that 2.4 gig radio. Support for up to 80 megahertz channels. We saw why that doesn't always make sense. 256 QAM, OFDM. Support for up to 8 spatial streams, but we never actually saw that in reality. But it makes for, can talk big numbers if we do that. But the real thing that we got out of this with the spatial streams, if you look at what was happening in the client space at the time, when we first started talking about Wi-Fi, it was all about laptops. But now it's all about mobile devices. And so those mobile devices typically don't have that many transmit-receive chains in it. And therefore, the number of spatial streams that we can support isn't there. So I can't send 3 spatial streams to a 1 spatial stream device. And so this I like to use to visualize. There's basically 3 dimensions that I have and looking at how I'm going to increase bandwidth. So right here, basically modulation, right? And what limits the modulation scheme that I can use? What did we say? Signal noise ratio, right? Channel bandwidth, that's going to be based on what country I'm in, what channels I have available, what other interference is going on. And then spatial streams, which ties to the number of device. So those are my three sort of dimensions that I have to adjust and figure out how much data can I cram in the pipe. Which takes us to wave 2, or I guess now we're going to start calling it Wi-Fi 5. So what brought in with that? Well, for starters, the idea of 160 megahertz channels, which we just saw in Australia, you get 1, so not really a big advantage for us, but again, lets us say things like big numbers, like close to 7 gig if you happen to have a theoretical 8 spatial stream device and could use a 160 megahertz channel. The real thing is multi-user MIMO. This was cool stuff. Quick story. When I came from Radiata, right? We did the first 11A chipset based here in Sydney. And when we first started talking to Cisco, they said, we make switches. Switching is good. We want switched wireless. We said, well, it's kind of a shared spectrum, so you can't really have switched wireless. And yet, here we are today with multi-user MIMO. This is switched wireless, right? Basically what I'm saying is if I can't use all 3 spatial streams to one client, well, why don't I do different spatial streams to different clients? And so now I'm able to sort of maximize that channel efficiency, and that's what it's about. It's about improving spectrum efficiency. I don't have this wasted potential because I have 3 streams that I can't use. It does not increase bandwidth or create spectrum. You really need to understand this as a basic concept. The bandwidth we have, the channels we have are what we have. It's all about how efficiently I can make use of it. And the real message here is you can't get more than 1 second out of 1 second of airtime. Okay? Very basic kind of principle. It sounds obvious until you actually have people trying to do more with, outside of the physical possibility of what you can do. Now, there's one last piece I want to talk about and sort of what we're seeing from a technology space from an 8 to 11AC perspective, and that's the idea of dual 5 gig. We're just starting to see a bunch of vendors come out with this, and it's not just a Cisco thing. The idea, again, is about improving spectral efficiency. So if you think about a typical high-density design, typically what we found was people had to turn off the 2.4 gig radio. Why? Because I only have 3 channels to play with. 2.4 also propagates broader, just from how the energy works. And so we ended up turning off all those or switching them into monitor mode. So the idea was, well, again, wasted potential. So we put 2 5 gig now in, and the idea is the first one acts as a microcell, similar to what you have on cell towers today. Okay? And the idea is that all the clients near the AP that are getting good signal quality, therefore able to maintain the high data rates, they're going to connect to that microcell. Then my secondary radio, I'll switch to 5 gig, and this will be my macro cell. So all you guys in the back that are not getting as good a connection to it and therefore at a lower data rate, rather than screwing things up for the guys in the front, we're going to give you your own dedicated cell, right? And that's, again, maximizing the efficiency. I can only get 1 second out of 1 second of airtime. So if you guys are chewing up the airtime with a lower data rate, by putting you on your own cell, we improve the utilization in the microcell. Make sense? All right. So that's where we are today. What's coming? Let's talk a little bit about 802.11ax, also known as Wi-Fi 6. First thing, when is it coming? Well, you're going to start seeing, we've already started to see some announcements in both the consumer and the enterprise space. I suspect certainly consumer players will want to have stuff for you to buy for Christmas. I just saw something from Netgear. It looks like an advanced TIE fighter kind of thing. The standard isn't going to finish probably until next year this time. In fact, it may actually slip into early 2020. The Wi-Fi Alliance will actually have their interoperability testbed, again, aiming sort of August, September next year. Need to see how that's split. Real quick, people know the difference between the IEEE and the Wi-Fi Alliance? Yeah, most of you, some of you? All right, real quick. The IEEE makes standards, otherwise known as reams and reams of paper. The problem with that is if you take a standard and give it to 5 engineers and put them in a room, you will end up with 10 implementations that don't talk to each other. Okay? So that's where the Wi-Fi Alliance comes into play. This is an industry standards body, and it's all about how do I make sure things actually talk to each other. So they develop not paper, but, well, they still develop paper, but test beds in order to test how things are working and making sure that things will interoperate well together. Okay, so that's why having the interoperability standard is important. Having an actual standard is also important. So what about all these devices that are going to come out at the end of this year? Probably see client devices at Mobile World Congress early next year in Barcelona. Look, what we know about the chipsets today is there are some chipsets, predominantly the ones that are 4x4. Those should be completely standards compliant. There's also some 8x8 chipsets, which we know don't have capabilities which are likely to be mandatory, and so those won't be. Basically, what I'd be looking at is, as you start looking in this space, one, if you're doing real advanced stuff, you're probably not going to want to do the first generation, to be honest. But two, just make sure you're asking the right questions and know what can be and cannot be, because at the end of the day, it's down to what the chipsets can do. All right, so that's enough on the standard side. But what actually is it? Well, first off, 2.4 and 5 gig. Okay, why are we going back to 2.4? A lot of the capabilities that we'll look at in a minute actually will give me effectiveness in the 2.4 gig band, even though I still only have 3 channels. And so looking at taking advantage of that. 80 plus 80. We actually talked about doing this with Wave 2. Again, never really materialized. The idea here is if I don't have that many 160 megahertz channels, maybe I can have non-contiguous 80 megahertz channels and still squeeze more bandwidth through. Again, usefulness is going to be mixed depending on the environment. Big change, 1024 QAM. You thought 256 QAM was complex. Now we're at this, right? Again, need better signal-noise ratio if I'm even going to hope to get this through. So how do I achieve that? Well, support for 8 spatial streams, but not in the way that you're thinking. Right? We already said my iPhone is never going to have 8 spatial streams. You know, maybe 2 at best. I think they got 2 in the iPads now, but you know, there's a limit to what you can physically cram into those devices. So instead, we're looking at that idea of the transmit and receive diversity. If I do 8x4, that's going to improve my signal quality at the receiver. I'm going to be able to support that 1024. Alternatively, I've still got multi-user MIMO. So yes, my iPhone only supports 1 spatial stream, but I can still now talk to 8 phones simultaneously. All about that channel utilization piece. One of the more interesting pieces, though, is we're actually going to change what's happening at the base level. Right? We're going to go from OFDM to OFDMA. So OFDM, we talked about that, Pink Floyd, got my subcarriers. The real limitation in what we're doing there is I'm still using all of those subcarriers for a single client device. The way I think about it is you've got a truck, it's leaving the station when it leaves the station, but it's only going to take something from one person, whether I can fill it or not. Right? OFDMA, the MA stands for multiple access. The idea here now is I actually can fill that truck with stuff from more than one person. So that's, again, going to improve that spectral utilization, allow me to cram more bits because now I can talk to more people. Lots more complexity in that, which I'm not really going to get into in the next 5-10 minutes. The last piece I want to just touch on briefly is focus on spatial reuse. And how many of you have heard the term BSS coloring? Yeah, comes up a bit. And I'm a bit hesitant because I didn't cover any of the fundamentals of this anywhere else, but let's just go through and see how we go. The idea really simply is if I'm going to transmit on this channel, I need to make sure no one else is transmitting on that channel. And so I have this concept called energy detect. Okay? And Wi-Fi, partly why it works so well, is because we're very sensitive to listening to energy on the channel. If I hear something, I'm not going to talk. The problem with that is there's a lot of dead airtime, and again, that utilization piece means that's going to be low. So the idea is, what if I can actually adjust when I actually detect it as energy that I can or can't transmit. Now, part of the problem is every AP is always at max transmit power. Now, we try to do clever things with radio resource management, but as I said, pointing the antenna at that metal plate, it's just math. If I don't have a high density design, well, then we're going to crank up the power in order to get the signal as far as we can. But what that means is now I've got to be very sensitive to that noise, even if it's another AP completely unrelated to my network, but on the same channel as me. So what we're trying to do is make it easier for people to say, hey, I'm going to transmit at a lower power, not because I'm not trying to get this big cell, but because all of my users actually are close to me and I don't need to go to that higher power in order to reach them. Now the benefit that you get for that trade-off is now I can adjust my threshold because I'm talking quieter, right? I'm not going to be necessarily interfering with the other guy who's somewhere else, and so now even though I hear him, I can still transmit at the same time. Okay, so the idea is, again, letting us kind of share the spectrum a little bit better. Of course, then the service providers are going to come in with LTE and they're going to screw everything up, but that's a separate problem for another day. Okay, let's sum it all up. I'm going to leave you with just 3 thoughts, which hopefully, as we go through this whole day and you see all these spectral diagrams and different colors and things like that, will help you at least have an understanding of what's beneath the hood of that. Right? Number 1, can't get more than 1 second out of 1 second of airtime. Sounds obvious until it's not. Number 2, you got 2 levers. What can I do? Increase signal and decrease the noise. All right. Last, number 3. In order to cram more bits, I've got 3 dimensions. They are channel bonding, modulation, and spatial multiplexing. All right? At the end of the day, that's how Wi-Fi works. Hope, they say a magician should never reveal his tricks, but hopefully I've given you a little bit of what's under the hood, how all this works, how you guys can make it work more effectively. Thank you very much.